very pleased to be here. This talk is
Thank you.
so this talk is a bit different. It's really how we can approach, I think, the materials that we're developing, and we heard could be the type of work that is being done here, but in most of your labs too, in a sustainable work. And this work, yeah, okay. So this work is based on my work and materials, but also I've been working with various organizations I created on the energy transition. So how can we transform our society at the macro scale to be able to reach our objectives in terms of greenhouse gas emissions? But there's more than greenhouse gas emissions. When you look at the population, for example, Canada's population will increase by about the world population will increase by about 25% by 2050, and could reach more than 11 billion people by 2100. In parallel to feeding and housing these population, it's important to think about climate control, and these needs will lead to a lot of disruption in the way we're acting and where we're investing money, and then the challenge of how do you reduce GHG emissions while doing your other tasks. One thing we see when we look at this energy transition is that it will require enormous infrastructures to be able to provide the energy, but also distribute it, in addition to the other infrastructure we'll need to meet this population growth. And so we cannot just do these infrastructure without thinking of their impact on the planet. Okay, we're already in a situation where biodiversity is being reduced rapidly, where we have environmental issues. So as we make these infrastructures, as we build this, as we think of new material, we cannot forget that we live in a planet that also is by our species quite significantly and being transformed also. So we need to be able to think about how will we think about materials in a world where we have also to worry about all these issues. So materials, we already had a bit of a brief history of development of material by Kilbeer, so I'll be about at the same level. The Industrial Revolution we started in the 19th century, where we discovered the periodic table. So development of steel manufacturing process, which are a major advance. Now with steel in 1855, it was possible to make the steel at a very large scale, and that really drove the development of the society we know today. At the same time, because we had steel, also reinforced concrete. Why am I talking about these materials that look like passé? Because they still represent today the majority of the material and volume that we're making by far. Okay. Once we had this periodic table, and it's amazing, you know, the development of the periodic table is a 1 century thing. Okay, at the beginning of the 19th century, we had about 15 elements that we knew. At the end of the 19th century, we knew almost all the periodic table. Not totally, but almost. And then, of course, we developed a lot of new materials at scale, so plastic, pesticide, the semiconductors, glass, alloys, composite, fertilizing. I mean, that's also a major production in terms of quantity. So essentially, today, we use all the periodic table almost, including many unstable elements. So this is a huge change in the way we see the matter around us and how we access it. But also it means that there's been huge changes in where we're looking for and what we are looking for in the crust of the earth in order to fulfill the need we need here in terms of materials. Okay. So it's important to realize that as we extract more and more of this matter, we have an environmental impact. And the environmental impact is very different according to what we're extracting. For example, if you're thinking of iron ore, iron ore is typically very high concentration of ore of iron and ore. So if you look, for example, at what we're extracting in Labrador and Quebec at that around Labrador, we have these ores about 60% rich, okay, which is extreme. So it's everything you pull out, essentially, it's iron that you use. If you compare with other, at the other end of the spectrum, for example, the gold that we're also extracting here, we are talking about 1 to 5 grams a ton, okay? So essentially for every ton of matter you extract from the earth, you generate 1 ton of residue and of waste, okay? Minus 1 gram. So the impact clearly on the environment is very different from these type of extraction. And that's at the extraction, but of course after that we're transforming it. At every level of transformation, we're also generating waste. And at the end, we also have complex materials that are more and more complex and that get harder and harder to recycle or reuse, because if you have 13 different elements in your apparatus, it's very hard to separate them unless you're moving back almost essentially to the source. If you think of cell phone thermal today, the way we recycle cell phone is we burn them and we essentially recover a few grams or less of expensive metal, from copper to gold, and the rest, and arsenic, we just let it go in the air. If you're hearing about this Glencore plant, for example, in Abitibi, this issue is that as we're burning foam, there's some bit of arsenic, and that's, we don't hear too much. So extraction causes irreparable environmental damage. That's life, okay? If you change something and you extract material, you are changing them. All this transformation will involve the polluting process. And the end of life also brings its share of contamination. The more also we move forward, the more we deplete the richer resources, richer settlement, and then we have to move to smaller and smaller concentration. So that means we have to generate more waste for the same amount of interesting material. I mean, gold was not always at 1 gram per ton, okay? But in the last 20 years, we've seen, in the last 100 years, we've seen this falling. Same thing for copper and other type of. If you look at the increase in materials, so I have the numbers until 2015, but you see that between 1970 roughly and 2000, the amount of matter that was extracted from the crust was almost constant as 10,000 million tons of material that we were extracting. And what happened here, early 2000? Well, you had China, in large part, who developed economically. And if you want to develop economically, you need to build infrastructures. If you build infrastructure, you need materials. And that's the growth we see here. And it's interesting, you see this nice slope, okay? So while we were on the slope, of course, all the experts were saying it will never stop, okay? The growth will be infinite, because it seems experts have difficulties understanding that trends will not be forever, okay? And of course, at one point you had built all the roads and high-speed train and everything you needed. So you see that it's plateauing, but there's still a lot of margin for growth. I mean, there's many regions in the world who have no or not much infrastructure as they develop building. So where am I going? Well, this is from iron ore. You see also the huge jump that happened in 2010 in terms of iron ore. And again, now we're plateauing, going down. But it's the same thing. At one point you stop, but it's still the level, the base level increases. So it's the same thing if you look at steel. So why am I showing all this, and what is the role of sustainability in it? So there's been a number of work, not as many as I would have thought, talking about what do we talk about sustainable materials management. And the idea is, how do we promote these materials in such a way that we are reducing the negative impact? and we want to preserve as much as possible the natural capital. So through life cycle of materials. So essentially the whole thing is how can we make sure we always recycle things. Okay. A lot of the focus is on this. If you look at this nice graph, so essentially you're harvesting, where do we start with harvesting? You're having renewable resource stock, non-renewable, and then you're transforming them through product supply chain with energy, because you need energy to do all this. And then you fulfill the demand, and then hopefully you will reuse this, recover this to be able to have this kind of nice cycle, virtuous cycle. Let me just go back to the energy. Okay. If you want to recycle, you need energy. The more you want to recycle, the more you reuse, the more energy you need. Okay, so there's this balance. If you don't want to spend energy, you cannot recycle. Okay, because we have complex materials. To undo them, take them apart, refine the elements, means you have to have. Okay, that's kind of basic thermodynamics. People forget that, because you have materials. Okay, well, thermodynamics is at the core of what we're doing. Reassembling elements is all about thermodynamics. And so the issue with these stuff that I've been looking at a lot is that they all tend to say we have the incoming materials that we need, and then it's all about what do I do after? Once I've built my semiconductor, once I've built my phone or whatever, what do I do after to be able to recycle? And I think there's a major issue here because it misses all the science with just one step. You have to be able to say, let me think about the materials from the onset about the service. And how can I deliver the service in a way that has the smallest impact, that has the materials, or the composition of this material, which has the least impact on society. And that means we need to think about reviewing even the composition, okay? How can I, for example, make a phone without using any of these rare elements, without using any of these, of the metals or the rare metals in the electronics, and still deliver the capacity to service line? If you do it, well, you reduce environmental impact before you're even starting to build something, okay? That's where you have the most impact. Not when you're trying to recycle. You have to say, how do I do it at the onset? How do I design alloys? I mean, if you think about car alloys, we know that we don't lose the steel that is in cars, okay? We recover it, but we never put it back in car. Because as we recover it, we mix it, and then we lose the high quality because these alloys are very sophisticated. So what we do is that we downgrade the use, and then we downgrade the use, and then at the end, it's just put in a reinforced, essentially in concrete reinforcement. Okay. That's where all steel adds up, So if you think of the alloy better, before you even start building the car, maybe this alloy can be recyclable, really, and move back. If you think about, is it a question of alloy? Can I rethink the structure of my steel so that the issue is not an alloy, it's the way I prepare my steel to have this nice composition. And to me, this is exciting science, okay? It's something that has to be done by us, not by anybody else, okay? And that means we know the service, but can I redo the service, understanding what happens in the universe, on the planet, and what's the impact of this technology on where I'm. And that means reinventing processes, rethinking the structure. So it's at all levels. And at all levels, you have to address barriers to change. So it's a way to think that is integrated, but where the fundamental researchers are at the basis of this, not as an afterthought. I'll give you an example, okay? So in 2002, the European Community introduced a restriction of hazardous substance directive, which targets electronics and says we should remove 10 hazardous substances, including lead and piezoelectric. So piezoelectric, are kind of, what it is. You deform them and you get the voltage.
And the best one are PZT, lead, zirconium, and titanium. So once they said we have to remove the lead in this, formally there's not much problem with lead in PZT. I mean, it doesn't leak or anything, but let's not talk about that. Okay. So of course it led to a lot of excitement from basic researchers said, wow, I can now justify the work I'm doing and get funding because I can look for new products. In fact, there's been a lot of new products that have been proposed. However, still today, in the last few years, what happened is that for 20 years, for another time in 20 years, the European has been pushing back the restriction of PZT. Why? Not because of the changes in technology, we've done many years, but because legally and structurally, it's very hard to leave PZT. Because if I have a car which is worth $50,000, and I have I don't know, hundreds of these piezoelectric, that cost me $1, okay? And if I want to change my PZT, I have to change the detail because not all these piezoelectric will work exactly the same, react at the temperature the same way and all this. So will I redesign a car which is $50,000 in order to be able to change a $1 piece of equipment, $1 piece of equipment? No, okay, unless I'm totally forced. And people who are making the PZT are using, there's no longer any intellectual property on PZT. They've been around for decades. Okay, so if you want to move to new technology, it means that these old companies who are used to live without intellectual property don't want to bother with, no, how do I do this? How do I get the patent and all this? Who will be the winner? So you have a whole infrastructure here that is resilient to the bright ideas that we're having. Okay, so having bright ideas is not sufficient. It helps, but it's not sufficient. Okay, so I told all this story here. So when I say we need to look at barriers, you need to think about the whole path of usage. Okay. Let me give another example. Okay, batteries. Batteries is very different, in part because it's very dynamic. Things are moving fast, and everybody has to work with intellectual property, and every company knows that their technology might not last 2 years. Okay, so it's much more amenable to these very deep and fast transformation because of this is not settled. I mean, typically a technology starts, nobody knows where it is. So for about 10, 15 years, things evolve rapidly. And at one point you kind of saturate, you corner the market, and then you stop doing deep innovation. So innovation dies slowly, okay? And then you're working at the margin without transforming anything in that. That's the challenge. So batteries is relatively easy. So we use cobalt in cathode. And this is often seen as a major risk in the supply chain for the cost, for how it is extracted, for environmental issues and social issues. So there's been many efforts to eliminate cobalt. We know that, for example, lithium iron phosphate battery seems to be one of the winning, and today half the Teslas, for example, are using this battery. So it's not something we're dreaming of. And then, it was for those who are not in Quebec, it was developed in part here at Quebec. So I have to put my chauvinistic hat for a second. And we can also look at other type of cathodes that could have problem, nickel-based cathodes, for example. So when you look at researchers, you see, for example, this great announcement a few years ago, cobalt-free cathode could lead to safer, longer battery. Okay, so that's great, we're getting rid of cobalt. That's where I would say that's the type of discovery that is for researchers, but it's just a way, how do I justify what I'm doing without thinking whether it's relevant? So when you look at what they put in, okay, magnesium, titanium is not so bad, manganese is okay, molybdenum, niobium. Okay, so now you're getting into elements that are far from better than cobalt, okay? So the issue is that even if we are full of goodwill, the idea is that to know where are the right solutions, what is a solution that matters, we need to know more than what we know in the lab. We need to be able to turn to structures, to places that can help us and say, okay, yeah, that's a bad idea, because if we put niobium, you're not out of the wood, okay? So how do we do this? And so it's very nice to say, let's researchers, let's do sustainable materials. But we cannot do it without depth of knowledge that is often totally outside our field. So there has to be some kind of discussion. It cannot be just led uniquely. So if you look at batteries, there's a lot of solutions that are being developed, but we need to be able to think, will these create new environmental problems? How do I think about that? Are there things I don't know about? So all these things are, how do we structure the knowledge around what we're doing to make sure we're not losing our time, or that we're at least applying the thinking in the right direction? How do we link, therefore, the basic science we're doing to how we move on supply chain and adapt, and how does that deliver? Another example, and that's where I come back to this fact that we have problems when we are extrapolating. Okay, so this is a report that was done a few years ago about the estimated demand for rare earth elements. Okay? Rare earth elements are at the core today of all the magnet that we're using in the cars, for the rotors, for the windmill. Okay? When you look at this demand, you see that there's an explosion coming, and we'll see we will ever be able to produce as much rare earth to even support this energy transition. So what's the solution? Well, for many people outside the materials, to say, let's find more of these rare earth, okay? Let's see how we can extract them. But as material scientists, another question is, do we need these rare earth? Can we rethink from the ground up the materials so that we don't need that? Okay. And I'm not only the one, no, other kind of less famous people have thought of it, like Elon Musk, for example, who just announced a year ago that they're going to EV motors with no rare earth. Probably it will be iron phosphate. Okay, it's not so clear the technology they're thinking about. So I know nothing about this. I read a bit on papers what people were saying it could be. So I don't know what it will be. But this would be major. Okay? A bit like the lithium phosphate. Once you show it's possible, you put a lot of pressure. No, these rotors are not only in cars; they are in all rotor, all engines, all motor, even the turbine, wind turbines, and all this. So if that succeeds and you can scale it up, you're transforming totally the impact and the cost of doing it, but also the environmental cost of moving forward, because you reduce enormously the demand for rare earth. Okay, what's the problem with rare earth is because you have 20 elements that are almost identical, okay, chemically. So you need like 10,000 chemical steps to separate these rare earths. So it's extremely toxic and extremely demanding to read. And they're not rare. We find them plenty all over the place. The issue is how to separate them. Okay? And I'm a physicist, so I really don't understand what's happening to really separate them, but I'll leave that with you. So to me, thinking about sustainable material needs to start before we first conceive the first object. When we think about the materials we're using, when we think of the structure, because here I talked about composition, but if you structure your material differently, you can also say, and I'll cite again Tesla. I mean, for 100 years, essentially the largest piece you could do in injected aluminum, okay, was about that big, okay, about 30 centimeters. Okay. Because you need to anneal, thank you, I should know that. You need to anneal the material and it will deform, okay, so you're stuck. But Tesla, when it came in with the car, essentially went and developed or bought a technology, an alloy, and a way of preparing the alloy that allows them to make full body in a single part of aluminum without having to anneal it and having the right strength. Okay. So this is not as much as allowing a bit of it, but also is how do you think about preparing the material? So it's very deep, it's very broad. And I think we need to understand, if you want to move in this life cycle, we need to understand what's the impact of what we're doing. We need to develop a better understanding of the physics. We know how to do something with one chemistry or one type of element or one structure. if we don't understand it fully, we cannot recover this by other means, by simpler organization. So there's a lot of exciting science there. And in terms of really deep science, we need to understand better if we want to. It requires exchanges at multiple levels. The material science scientists will not do all of that. Of course, we don't want to talk to sociologists too much. But the idea is that we still have to be there, I think. And looking like this, we could make significant impact in the way as we grow the use of materials of more sophisticated use, we still reduce the environmental impact of it. But for this, of course, we need to be able to develop structures, capacity to think, to integrate, and help us orient ourselves through this maze of materials and transformation challenges. So I'll stop here. No, so we need development at all scale. We think a lot about the small thing, but there's a lot of materials that are at very large scale. So I'll stop here for real. Thank you very much.
Thank you, Robert. Amazing talk. Questions? Oh, there.
From a practical, it was fantastic. So last slide about how you get all of these various people together, lawyers, sociologists, economists, etc. Practically speaking, what's the best way to actually do that? What's the best venue? What's the best?
I think you need an institute or something. You need to structure places, not one, but around the world, to start of this thing and integrate on it. All the thinking today has been led by engineers and above, where it's all about how you recycle. It's really, all the ideas, can we reinvent the material, is essentially omitted in all, most of what I've seen. Yeah, didn't see anything where you integrate the fact that you can rethink these things. And so, but this has to be supported because you cannot have every single material scientist spending their time thinking about that. So you need to do some of this work somewhere.
Maybe as a follow-up, it seems to me like students are going to have to do, what percentage of their training should we sacrifice so they actually become more familiar with these issues?
I mean, it could be relatively little if you have data and you have the capacity to get this information. I mean, the more and more we work with other people, so you have to collaborate. And if you have people who have this knowledge, they can help say, no, those are the issues. And then you go back in the lab and do your part where you are the real expert. You cannot think that everybody will become an expert at life cycle and at the same time be able to manage this sophisticated analysis.
Right.
It was very wonderful presentation. So at another higher level, we have this vision as whether we should have legislative action to force change or we should have incentive action. And which do you think is more effective, like monetary incentive subsidies or legislative requirements?
Both. I mean, the real world is complex and essentially, typically you need to throw almost everything. But one of the big issues, how do you remove a regulation? How do you change regulation? Okay. If you have the regulation for concrete as it is today, all the weaknesses are taken as normal in the concrete, and all the strengths are taken as essential. The way you change and you have a new recipe for concrete that doesn't have the same strength and change it, suddenly it fails. All the tests because you have all designed to support what we have today. So this is a big challenge is how do you also integrate this level? I mean, aeronautic was greatly innovative 50 years or 60 years ago. Today, getting a new material in aeronautics is a pain, okay? It's very hard.
Alex.
Yeah, thank you, first of all, for the very interesting and very important talk. I have a question about the recycling and with the idea of reducing extraction, etc. Would you say that there is a scientific gap in better, more efficient ways of reusing, recycling materials with the purpose of actually avoiding extracting new material?
The issue is cost, okay? If I'm extracting iron ore at 60%, okay, and I have a process very finely tuned to get my nickel out, now I get waste from which I don't know the details, okay? The issue I hold with batteries, everybody will say, will we be recycling batteries from cars and all this? Yes and no. I mean, if we know the battery, how it is made and everything, it will be easier, but easy. But now I get batteries from 5 different car manufacturers with 10 different technologies. Extracting and recycling with high efficiency gets much more expensive. So the issue is really waste. That's a big problem. So that's why you need to streamline this thinking from up front, not at the end. If you start thinking of it once you get the material in the dump, it's too late.
Okay, so Norman, I will go back to similar idea about Bart's topic. So Canada has started this minerals initiative, which critical minerals initiative. They made the policy over a few years, but as much as I know, they didn't consult any of the university people.
That's a standard. Canada doesn't believe
Yeah,
in
so
university.
exactly, that is where I'm saying, we are talking about this, but we have no influence from the governmental side. When they changed from, Kirk knows this, more personal nature kind of things. When they changed from the funding mechanism for alliance grant versus CRD grants, we were some of the people who were hesitant to go that route, but nobody listened. So we are talking about this, but they don't even respond to us. Whether they are open to even talking to us, that is a very big question. So how do we influence any of this?
I think we need effort. So I'll be brief, but I created the Energy Modeling Hub, which is a structure funded by Natural Resource Canada to support energy model and data that goes for the energy transition. So not energy at the level we're talking, noise climate, but how do we decarbonize all of Canada? This took us about 3 years, okay? We organized workshops, we invited people, we had experts with people from the government to move on this. It's not something that happens overnight. So you need concerted effort. I had the advantage now I'm heading the Coty Energy Institute where I have funding. So I can organize workshops, I don't care. So I have some freedom, but this is the type of things we need. And, but it could be something, we get a few researchers and we just drive this by repeating and getting to know who in the government that in our county is interested. And then they can get some money to start.
Last question.
Do you think that advanced research data management, including problems tracking, could improve the problem of recycling? So we know every single step the product was made and to follow it back.
The best knowledge you have, yes, but it's still, if I have 15 different things coming to my place, do I have to send them to 15 different plants across the world? I mean, that increases cost. So the issue is always, and in many cases, it's much cheaper to buy new material than recycle it. That's the issue of, you know how it comes, you know it's 99.9% pure, you don't worry, you go for it.
Yeah, so it's not suitable for batteries, but might be for other.
Absolutely, absolutely.
Yeah.
Batteries, I think we will be able, because even this, there will, I mean, now it's changing quickly, but there's not so many. But in 15 years, we'll standardize the technology. So we'll have a few dominant technologies. So I'm not too worried about, in cars, we don't lose them. It's not like cell phones. And you need to have more standardized technologies because of scale and also because of safety. So a phone, you don't care if it explodes. I mean, we'll just change the model in some way. But a car cannot explode. No, it's hard. It's more expensive. You have to change every car. And no, all this means that you change less when you get that sort of thing.